guys. Okay, so it's an honor to speak after so many really excellent and exciting talks. This has turned out to be a great conference. And so I want to kind of go in a different direction than most of the talks here, in that I will not be talking about hydrides. First, let me acknowledge all of the people who made this work possible. Largely, the work is a collaboration with Richard Hennig, Greg Stewart, and Peter Hirschfeld. But a number of other people have been important, including my two first grad students, Derek and Daniel, who built up my lab, and a very productive collaboration with Ravi Kumar and Russ Hamlin for X-ray measurements. And most of the results I'll be showing, many of them were collected by Isaiah Lim, who's a very talented postdoc for setting up, high pressure cells and electrical resistivity measurements, who will be looking for a position soon. So if you're looking to add a member to your faculty with high pressure skills, he would be an excellent choice. Yundi Kwan and Ajinkya Hai are also two postdoc and grad student who were involved in much of the theory work. So, okay, so let me begin by kind of talking about why we might be interested in non-hydride still, even with all the exciting hydride results. I'll talk about some tools we have for the synthesis of metastable materials, and then a couple of particular areas we've been looking, including in beryllium-rich materials and diborides. So to kind of set the stage for why we might be interested in non-hydrides, I think this example, which is a very large-scale example of the use of superconductors, is the ITER, which is this fusion reactor. This is a photo, I believe, after they cooled down this magnet for the first time. And this project procured some 500 tons of superconducting wire over a period of several years. This wire is made of a very old kind of superconductor, an A15 superconductor that's been around for quite some time. But if we think about, let's think a little bit about how this kind of material will be used. So it's going to be made in some plant in some far off location. It's going to be shipped on a truck at ambient conditions. It's going to be hot. It's going to be cold. It's going to be dry. It's going to be humid. And then it's got to sit there for a few years until it gets wound into this device. So that's what we're really looking at when we talk about applications. Now, when we talk about hydrides, and I hope you'll all forgive me for kind of taking a shot at hydrides. I, of course, think the work is extremely exciting. I'm merely trying to motivate why I'm talking about relatively low temperature superconductors at this conference, where there's so many exciting high TC hydride results. So if we look at applications of hydrides, kind of generally speaking, what are they? Well, reducing agents, bases, desiccants, hydrogen storage materials. And so what is common about these applications? Well, they involve a high degree of reactivity of the hydrogen, or in the case of hydrogen storage materials, the ability of the hydrogen to move in and out easily from the material. And so while I think it's likely that we may see hydrides quenched down to very, very low pressures, I think that putting these into applications where they can go through all of the trials and subject to high temperatures and humidity, et cetera, that we see are necessary to actually use a material, I think that's going to be a really big challenge. And so I think there's still a reason to look in non-hydride materials to see if some of the ideas that have developed here in hydrides can be employed for non-hydride materials. So one example that we have been interested in is niobium-3 silicon. And so I want to bring this up merely as an example of what a metastable material really is, what we really mean by metastable. So niobium-3 silicon in the A15 structure is predicted to have a TC of 25 to 31 Kelvin. Unfortunately, it doesn't actually crystallize in this A15 structure. It instead crystallizes in a tetragonal structure. And in fact, even this tetragonal structure is metastable. If you look at this phase diagram over here on the right, if you were to anneal it at, say, 1600 C, it would decompose into niobium-5, silicon-3, and niobium. So let me talk about what we did here. So in 1981, Ollinger and Newkirk synthesized the bulk phase by shock compression of the tetragonal material using plastic explosives. So they basically blew up a small bomb around the material. It took it to very high pressure, estimated to be around 1 megabar, and very high temperature, around 1000 C. And specific heat measurements showed a very nice specific heat transition, but the TC here was around 18 Kelvin. So again, the prediction was that it could be up around 25 or 30, but it was instead down around 18. And so the question was whether we could obtain a higher TC by recovering a less disordered sample from a static compression experiment. So this shock compression is very violent. Could we do a better job with static pressure? And some computational results showed that this cubic A15 phase should become stable above about 15 GPa. So let me describe the experiment we did. We took the explosively compressed explosively compressed sample, and the first thing we did was anneal it at room temperature for 39 years. So this sample was made some time ago. We then remeasured the sample some 39 years later, and it still showed a perfect bulk superconducting transition. So this is really stable, even though it's not the stable phase, it persists over a very long period of decades. We then did some megabar resistivity measurements, both on tetragonal and the A15 niobium-3 silicon phase. And so on the left here, we have resistivity measurements versus pressure on both the A15 phase, that's the one that was recovered from the explosive compression experiments, and the tetragonal A15 phase. And the phase diagram is here on the right. And so what you can see is that the TC of the A15 phase goes down. And then we look at the TC of the niobium-3 silicon phase, and this shows basically some niobium impurities. Now, this A15 structure is supposedly stable above 50 GPa, so we might expect that it would convert to the A15 phase, and we would see superconductivity from the A15 phase. And if we could then release the pressure, say at low temperature, we could recover the A15 phase. Unfortunately, what we find is that that does not happen. So this lower right diagram here with these arrows show sort of where you would expect the A15 transition to be if it were there, and it does not appear. And so it seems that tetragonal niobium-3 silicon doesn't convert to the high TC cubic phase unless you apply both heat and pressure together. And I think this is an important point, that if we have some kind of barrier for a transition going one way, it's not a foregone conclusion, but often the barrier will be of a similar magnitude for the transition going the other direction. And so if we really want to recover phases to ambient pressure and have them stick around for a long period of time, we may be interested in systems where we have to use high temperature in combination with pressure. So in this case, room temperature, even though the A15 phase is the stable phase, it was not enough to overcome the barrier and convert the tetragonal to the A15 phase. Okay, so let me talk a little bit about some tools, various tools for the synthesis of metastable compounds. And there are a lot of them out there, but I'm just going to talk about a small segment of them that we're interested in. And so one thing we've been exploring is cryogenic compression. So rather than applying pressure at room temperature or even liquid nitrogen pressure, we can apply pressure all the way down to about 2 Kelvin. And we do this continuously. So one thing we've been using for very quick and dirty measurements, we've often been using these designer diamond anvils where the electrical probes are kind of built into the anvil. And those allow you to set up an electrical resistivity measurement very rapidly. These are kind of hard to come by, so we generally don't use these above about 30 to 50 GPa because we don't want to damage them. But I think there's a lot of potential in these kinds of designer anvils. So here the probes are actually encapsulated inside of homoepitaxial diamond deposit on top of the anvil. And so there's a lot of opportunity here for incorporating different kinds of probes. Yogeshwar has put coils in these. Heaters are a possibility. So these modern nanofabrication, microfabrication techniques have a lot of potential to add new probes to high pressure measurements. We then use a standard membrane-driven diamond anvil cell. So this membrane is filled with helium gas, which means that as long as we keep the pressure below about 25 bars, we can adjust the force applied to the diamonds at any temperature down to low temperature. Rather than a simple knob on a gas bottle, we use this PACE 5000 pressure regulator. So this is basically a computer-controlled pressure regulator that lets us program in a sweep so we can very gradually sweep the pressure even at low temperature. This is all coupled to a system that does automatic real-time pressure determination by measuring the ruby fluorescence and then fitting a peak function to the peak. It takes into account the temperature correction to the ruby signal as well. And so, for example, one of the things you can do with this system is sweep the pressure at low temperature and see a superconducting transition as a function of pressure at constant temperature, rather than the common feature you see of sweeping temperature at constant pressure. And so this is something we've employed in a number of different cases. This one I'm showing here, bismuth 2 tellurium iodide, we actually discovered 3 different related materials, all that exhibited pressure-induced superconductivity. At room temperature, we find some other anomalies in the resistivity. So it turns out that this transition is connected with a structural transition that still occurs even during low temperature compression. And so this is a useful tool, one, because it allows you to very rapidly screen something for pressure-induced superconductivity, but two, because it can lead to different phases during low temperature compression. And I'll talk about that for a moment. So one of the interesting examples we've found of that is this case of metastable barium-6. And so on the left here, you see the structural phase diagram of barium. This is not our work. And there are a number of different phases here. The ones that had previously been known before this study were barium 1, 2, 4, and 5. I believe barium 3 is way up at higher temperature. But what was found was that there is this very unusual barium 6 phase that only appears at low temperature, but it doesn't appear at low temperature if you cool from high temperature. So for example, if you go to 20 GPa at room temperature and cool down, you do not find superconductivity. Or you do not find this barium 6 phase, excuse me. However, if you first cool down to low temperature at low pressure, say at 5 GPa, and then you start increasing the pressure, you can enter this novel barium 6 phase. And so we wanted to see if perhaps this barium 6 phase would have a different superconducting behavior than barium-4. This was the previous work on superconductivity in barium. So basically it becomes superconducting in barium-1 and gradually rises. And then within the barium-4 phase, Tc kind of gradually decreases. So that was the previous work. And whoops, I'm going backwards. So what did we find? We found, if you look here on the right is the phase diagram. So the gray curve is the result that was obtained when you apply pressure at room temperature, kind of the standard approach to these kinds of measurements. In contrast, when we apply pressure at low temperature, we get a significantly enhanced TC. And this was confirmed both in electrical resistivity and magnetic susceptibility measurements. Here are some magnetic susceptibility measurements where you see both you see the transition both in the real and the imaginary part of the data, which is often this imaginary part is not shown. And so, of course, 8 Kelvin is nothing particularly exciting, but what this shows is that cryogenic compression has some potential to find new superconducting phases. And in fact, the very next sample we studied using this approach exhibited quite similar behavior. So this is strontium, which we've just performed some X-ray diffraction measurements on. But essentially here we find the blue curve being our data obtained by cryogenic compression, substantially enhanced TC over this strontium-4 previously observed critical temperature. And it turns out that what appears to be going on here is that the strontium-3 phase is persisting to higher pressures than previously observed. So basically, we've taken this slope, what appears is happening, we've taken this slope for strontium-3, and when it would normally transition to a phase with a lower TC via cryogenic compression, we've kind of continued to push TC higher. So I think these approaches have some interesting possibilities. And the fact that the first two things we looked at both displayed this kind of behavior is quite interesting. So there are other exciting methods that I want to point out. So there's been some very nice recent work by Paul Chu's group on rapid pressure quenching. And so for those of you in the audience who are not familiar with with steel and the science of steel, some of the key facts about producing high strength steel are described in this figure on the left, which is a temperature time transformation diagram. So essentially, if we go to say 500 C and we begin annealing the sample at constant temperature, after some 10 seconds, the sample begins to convert to some combination of perlite and bainite. And so if you want to avoid that conversion, you have to quench the sample very rapidly along one of these dashed lines. And you can see that there's actually a temperature range where the conversion happens most rapidly. It doesn't continue to occur more rapidly at higher temperature. This may be slightly non-intuitive. And so what Paul Chu has done is he's created a system that allows him to very rapidly change the pressure. So this is kind of the pressure analog of the approach to steel here. And here's an example he showed for the TC of iron selenide, where the blue data points here are TC under some applied pressure, right? And the red and green points are the TC that he gets at ambient pressure after quenching from the pressure shown on the phase diagram here. So if he quenches from 4 GPa at 4.2 Kelvin, he rapidly reduces the pressure. They can bring the TC, this high 40 Kelvin TC that's normally only observed at high pressure, all the way back to ambient pressure. And so this approach of very rapid pressure changes, I think, shows a lot of promise, and I think this is something we'll hopefully see more of in the future. There are, of course, other interesting methods, some of which have been talked about at this conference and elsewhere. So, for example, Russ Hemley talked about electrochemistry. Of course, there's the use of light. So, compared to temperature, the energy in a photon is quite large compared to room temperature. So I think these other approaches to producing metastable structures, getting over energy barriers or preventing yourself from going over an energy barrier are quite important and interesting. And it's something that my understanding is that the theory, it's a difficult problem for the theorists, but I think it's something worth trying to make headway on because there's a lot of phase space for us experimentalists to explore here. Okay, so let me now move on to some low Z materials as promised. So I hope you'll forgive that this slide is possibly a little out of date and I haven't provided the full author lists on all of these slides. But one thing that's striking to me about the hydrides is that these high TCs appear to be rather ubiquitous. When you look in some of these papers, you will find very many different high pressure phases predicted to exhibit quite high TCs. So hopefully this is not too small to read, but circled in red, we have a number of different predicted TCs, spanning the range from 10 Kelvin up to around 200 Kelvin. And this occurs in a very wide range of different structures. So there's, of course, some resemblance between many of these structures. They have some kind of cage-like appearance, but these are not identical structures. And this is somewhat in contrast to, I think, what my feeling is for how superconductivity has worked in other families of superconductors, right? So if you look at the cuprates have this very similar structural motif of the copper oxide planes. The iron-based superconductors have these very similar planes, and the different members of the families are just different stackings of these planes with interlayers. The A15 superconductors all share this A15 structure, and if you move outside of that structure, it often leads to a drastic reduction in TC, or in the case of iron-based superconductors, it's this structural motif that's important, and as soon as you move away from that, the superconductivity disappears. So this is surprising to me, and it kind of suggests that they're just too important to vastly oversimplify all of the exciting and careful, interesting science that's been presented at this conference. There are two important things. One is you need quite a bit of hydrogen, and maybe you just need something light. So maybe you just need a light element and quite a bit of it. So, of course, even H3S has more hydrogen than usual. And so this kind of spurred us to test this idea. Is it just that you have a lot of something light? And can we get similarly high transition temperatures by having a lot of something light and high pressure, of course? High pressure seems to be another important ingredient. And so what we decided to look at were beryllium-rich materials. And so, of course, there's been work in other light element compounds like MgB2. I'll talk about that a little more later. But beryllium has this very appealing feature that it tends to form very, very beryllium-rich compounds at ambient pressure. And if you superficially look at some of these structures, they look not so different from these clathrate structures that you see in the hydrides. So we have these rheniums surrounded by cages of beryllium in this material, beryllium-22 rhenium. So the question was, if we take these up to very, very high pressure, are we going to start to see some high critical temperatures? And so we've done a fair amount of work in this area looking at a number of different beryllium-rich materials. Beryllium, as you may know, is rather toxic, but our member of our team, Greg Stewart, has a lot of experience synthesizing beryllium materials. Once you put it into a compound, it's not particularly hazardous, as many of you know from working with beryllium copper pressure cells. So what did we find? So I'm going to go through a few different examples here. So the first example was gold beryllium. So this one is not particularly beryllium rich, but it was one of the earliest ones we synthesized. It's actually superconducting at ambient pressure with a TC of 2 or 3 Kelvin. And the basic result we found here was that TC very rapidly went down and did not reappear all the way up to at least 140 GPa. The structural predictions here were interesting in that they suggested that at high pressure, this material ought to decompose. There's some indication of a kink in the residual resistivity as a function of pressure at around the pressure when we think it should be, this ambient pressure phase should be becoming unstable. But the X-ray measurements don't seem to support that. So again, an interesting result, but TC went down and it never came back and got high. But maybe we just didn't have enough beryllium here. So let's look at something more beryllium rich. So here are two materials that are have a larger amount of beryllium in them. We've got here, just move this out of the way. So beryllium 5 platinum. So this is a rather unusual material, but under pressure, it seems to become less metallic. So the resistivity at low temperature actually goes up. In this case, we only studied it to 31 GPa, but computational results suggested we shouldn't expect much exciting to happen at higher pressure. In the case of beryllium 13 calcium, this is a material with a much larger amount of beryllium in it. Here we studied the material all the way up to 171 GPa. This, by the way, this is not our figure here. This structural diagram in the lower left of the right-hand panel, it exhibits this similar kind of class rate like cage structure, but no superconductivity up to these very, very high pressures. So let's, again, maybe we just don't have enough beryllium. So here is beryllium 22 rhenium. And here we've got some superconductivity. It starts off, this is actually one of the highest TCs at ambient pressure among beryllium-rich compounds. And the electrical resistivity transition starts off at about 8 Kelvin, and then just moves monotonically down to about 6 or 6.5 Kelvin at 30 GPa. In this case, we were able to get some X-ray results up to 160 GPa, and in fact, the structure just doesn't change at all. So the beryllium here is quite inert under pressure. So in contrast to the hydrides, where you get these very different kinds of structures as you go to high pressure, beryllium just seems relatively inert under pressure. The structure doesn't change, and the TC does not go up. Okay, so again, there seems to be more, which I'm sure many of you in the audience can help explain why that is, but there's more to high TC than just light elements and very high pressure. I think another interesting thing to point out is something I didn't appreciate at the beginning of this whole saga of beryllium compounds. But although the structures look very similar, and you see these numerous computational results on hydride, and as an experimentalist, you might say, well, why don't you try the same thing on beryllium compounds? And it turns out that's not feasible, as I understand it. So the additional electrons in beryllium, even in binary beryllium compounds, simply make this kind of work where you're computing TC for a wide range of structures impractical. So the situation with hydrogen, I think, is really very unique in that the calculations seem to be relatively feasible for systems with large unit cells. And this is something we don't see in other places. But of course, if the computational capabilities could be extended into other materials, I think that it would be quite exciting to see if there are other kind of corners of the periodic table where superconductivity appears to be so ubiquitous.
Excuse me, Jason.
Okay, so let me now. 5 minutes, okay. So I will quickly go through this last part here. So the very first thing I did in my career in high pressure was to study the pressure dependence of magnesium diboride. And so this material was reported with a lot of fanfare, and I think there was a lot of excitement that maybe there would be other related materials, that it would be possible to raise TC. It turns out that no matter what you do to MgB2, TC goes down. So here's a result from one of my first papers where we showed that TC goes down under pressure. Subsequent studies found the same thing. And it turns out that it's very hard to substitute on MgB2, but anything you put into MgB2 causes TC to go down. So it's sort of a snowflake, or it perhaps appeared so until recently, this study that just appeared in 2021 showing that molybdenum diboride under pressure exhibits TCs as high as above 30 Kelvin. This phase at a high pressure appears to be an MgB2-like structure. Although I will say that some work by Yundi Kwan and Warren Pickett indicate that the superconductivity is really quite different in molybdenum diboride than in MgB2. In any case, Yundi did some, very quickly after this was discovered, did some calculations that indicated that WB2 would be the next best material to look at in terms of TC next to molybdenum diboride. And so we followed up on that with electrical resistivity measurements, almost to 200 GPa. These measurements showed a superconducting behavior with TCs as high as about 17 Kelvin. Transition is suppressed in a magnetic field. We followed this up with a structural study to see if this appearance of superconductivity was connected with a structural transition. And I'll skip past the gory details, but the answer is that this material does not adopt the MgB2 structure at high pressure. The X-ray measurement suggests that it stays in this ambient pressure HP12 phase, shown here. It's a little planes. It does not enter this HP3 MG2-like phase at high pressure. So why then is superconductivity appearing? Well, our collaborators did some, Vinkia and other members of our team worked on of TC, predicting TC for the various different structures that appear. And in fact, the only one that seemed to show a significant TC was this HP3 MgB2-like phase. All of the others showed very low critical temperatures. The HP3 phase supposedly becomes stable above 120 GPa, but again, it seems like a similar situation where without heat, we were unable to convert the sample fully, to this more stable phase. I will speak about this very briefly, but what we think is happening is that there are stacking faults and twin boundaries in the material that are MgB2-like. And that disappear at high pressure may be a for superconductivity that we're seeing. So we're continuing work in the diboride vein. There are a lot of possibilities for different things to do there, and attempting to stabilize the metastable high pressure superconducting phase at ambient pressure. So there'll be more to come on that in the near future. And just to summarize, sort of 3 points, it's not just the pressure and temperature, but it's the route that you use to get there that's important for what phase you get. Beryllium is definitely not hydrogen when it comes to high critical temperatures. And finally, I think there are a lot of opportunities in non-hydride low Z materials that I hope continue to be explored. Okay, thank you.